Here's something the AI hype machine doesn't want you to think about. Every single AI model you've heard of, GPT, Gemini, Claude, Grok, Kimi, all of them run on the same fundamental architecture invented in the 1940s. Binary logic, transistors, classical bits, ones and zeros. And right now, in labs in Delft, in Pasadena, in Zurich, and in Tokyo, scientists are building machines that don't use ones and zeros at all. Machines that can exist in all possible states simultaneously. Machines that, according to Quantinuum's lead architect Anthony Ransford, would require you to harvest the energy of every star in the observable universe just to replicate what their quantum processor did in a single session. Let that land for a second. Every star in the universe. This isn't science fiction. This is November 2025, and it's just one of 10 discoveries we're covering today. Discoveries that don't just advance computing, but redefine what computing is allowed to do. Today, we're going deep into quantum computing. Not the basics, not the buzzwords, the 10 most significant discoveries from the last 12 months that signal a genuine paradigm shift. The kind that doesn't happen every decade, the kind that happens once per century. Let's go. Most people assume the quantum internet is a 2040 problem, something for the next generation to worry about. In September 2025, Penn State engineers deployed a silicon Q chip, a quantum networking device, directly onto Verizon's actual fiber infrastructure. Not a lab, not a simulation, Verizon's actual network carrying real traffic. The chip uses the same internet protocol as the modern web, meaning it doesn't require a separate quantum network built from scratch. It plugs into what already exists. Why does this matter? Because quantum communication is theoretically unhackable, not very hard to hack, physically impossible to intercept without detection. The moment someone tries to eavesdrop on a quantum signal, the quantum state collapses and the intrusion is immediately flagged. For banking, for defense, for medical records, this isn't a feature upgrade, it's a security revolution. Now here's the dirty secret of quantum computing that hype videos rarely mention. Current quantum computers operate at temperatures colder than outer space, around 15 millikelvin, roughly 460 degrees below 0 Fahrenheit. The cooling systems alone cost millions and fill entire rooms. In December 2025, Stanford materials scientists published a breakthrough in Nature Communications. They built a nanoscale optical device made from molybdenum diselenide that achieves quantum entanglement at room temperature. The device uses what they call twisted light, photons spinning in a corkscrew pattern to entangle the spin of electrons. No cryogenic cooling, no dilution refrigerators. Lead researcher Jennifer Dione put it plainly, maybe someday we could do quantum computing in a cell phone. That's a 10-year plan, but the physics now exists. The bottleneck isn't theory anymore, it's engineering. And then there's scale. In September 2025, Caltech researchers split a single laser beam into 12,000 individual beams to trap 6,100 cesium atoms, each one acting as a qubit. That's a record, but the record isn't the interesting part. The interesting part is that these qubits stayed in superposition for 13 seconds, 10 times longer than any previous neutral atom array. And more importantly, the researchers could physically move the atoms around during computation. Why does that matter? Because one of the biggest bottlenecks in quantum computing is error correction. When qubits are fixed in place, fixing errors requires complex routing and massive overhead. When you can move the qubits themselves, like rearranging pieces on a chessboard, error correction becomes dramatically more efficient. This is the kind of architectural shift that turns quantum computing from a fragile experiment into a scalable machine. And this is only discoveries 10 through 8. AI is powerful software running on old rules. Quantum computing follows different physical rules entirely, and in 2025, those rules started working outside the lab. The countdown has only just begun.
Let's continue with discovery number 7. In February 2026, scientists at ICMM-CSIC in Madrid pulled off something physicists had talked about for decades but never proven in the lab. They successfully read a Majorana qubit. That alone would be newsworthy. What makes it historic is how this qubit stores information. A Majorana qubit doesn't keep its data in a single fragile spot. Instead, the information is split across two linked quantum states at the same time, known as Majorana zero modes. Because the data is distributed, everyday disturbances like vibrations, temperature shifts, or electromagnetic noise can't easily damage it. To actually corrupt the information, you'd have to hit both locations at the exact same moment. In practice, that's incredibly unlikely. Researcher Ramon Aguado summed it up perfectly when he called it a safe box for quantum information. The team measured parity coherence lasting over 1 millisecond. That sounds tiny, but in quantum computing, it's a serious sign of stability. Microsoft has been betting on this approach for years, releasing the Majorana 1 chip in 2025. Now the underlying physics has been independently confirmed. Topological quantum computing is no longer a theory on slides, it's real. Discovery number 4 is about proof. Since 2019, we've heard endless claims of quantum supremacy. The problem was trust. Most of those results couldn't be independently verified, so the debate never really ended. That changed in October 2025. Google ran a test where their quantum computer outperformed the world's fastest classical supercomputer by a factor of 13,000, using a verifiable algorithm that any research group could test for themselves. IBM pushed this further. In November 2025, they unveiled the Nighthawk processor with 120 qubits and 218 tunable couplers and submitted their results to an open, community-run quantum advantage tracker. Not a press release, a public benchmark. IBM's stated goal is verified quantum advantage confirmed by the wider scientific community by the end of 2026. And this isn't staying in the lab. HSBC is already using IBM's Heron processor to improve bond trading predictions by 34%. Ford Otosan cut factory scheduling from 30 minutes to under 5 using D-Wave's quantum annealing, and that system is in production. The era of quantum is coming is over. Quantum is here. Discovery number 5 shows what these machines can actually do. In November 2025, researchers demonstrated scalable quantum circuits that simulated fundamental nuclear physics on more than 100 qubits, preparing quantum states that classical computers simply cannot reproduce. This isn't about speed, it's about possibility. Classical computers approximate quantum systems, and those approximations get worse as complexity grows. Quantum computers don't translate quantum physics into math. They are quantum systems themselves. They simulate reality directly, like a mirror reflecting a face without distortion. That changes everything for fusion research, material science, drug discovery, and for understanding the forces that hold matter together. For the first time, we're building machines that operate in the language of the universe. Discovery number 4 removes the final barrier, scale. For decades, quantum computing faced a brutal problem. The larger the system, the faster errors piled up. It was like building a skyscraper where every new floor weakened the foundation. In 2025, that flipped. IBM demonstrated real-time error decoding in under 480 nanoseconds using QLDPC codes, a far more efficient form of quantum error correction, achieved a year ahead of schedule. Fred Chang put it bluntly, we're now in the era of escape velocity. Building a large, useful quantum computer is no longer a physics problem, it's an engineering problem. And engineering problems get solved with money,
talent, and time. IBM is targeting a fault-tolerant quantum computer by 2029. IonQ plans 1,600 logical qubits in 2028, scaling to 80,000 by 2030. The physics ceiling is broken. What comes next is construction.
Let's continue with discovery number 3. Quantum AI, the convergence that changes everything. Here's the thing most AI commentators miss entirely. AI and quantum computing are not competitors. They are convergent technologies. And that convergence is already happening. In November 2025, Quantinuum, the company that claims its Helios processor would require the energy of every star in the universe to replicate classically, partnered with NVIDIA to accelerate quantum generative AI through a platform called NVQLink. This isn't theoretical. Amgen is already using hybrid quantum machine learning for biologics research. BMW is running quantum simulations on fuel cell chemistry. JP Morgan Chase has conducted commercially relevant quantum research on the same platform. A May 2025 survey of 500 global business leaders found that 60% are actively investing in or exploring quantum AI. McKinsey estimates quantum computing's unlockable market value at $250 billion across pharma, finance, logistics, and materials science. But here's the number that should stop you cold. Quantum computing companies raised $3.77 billion in equity funding in just the first 9 months of 2025. That's nearly triple everything raised in all of 2024. The smart money isn't debating whether quantum will matter. It already moved. Now discovery number 2. Quantum sensors are rewriting what measurement means. This one doesn't get enough attention. Quantum sensors don't compute, they measure, with a precision that makes every existing instrument look like a sundial. In 2025, quantum sensors crossed into mainstream deployment. Quantum-enhanced atomic clocks are now accurate to 1 second in 300 million years. Quantum gravimeters can map underground structures, pipelines, aquifers, and geological formations without drilling a single hole. Quantum magnetometers can detect brain activity with a resolution that makes current MRI machines look blurry. The UK's National Quantum Technologies Program has already deployed quantum gravimeters for infrastructure mapping. The US military is funding quantum inertial navigation systems that work without GPS, immune to jamming, spoofing, or satellite outages. When you can measure the world with quantum precision, you don't just improve existing applications, you enable entirely new ones that were previously impossible. Now discovery number 1. Q-Day is no longer a theoretical threat. It has a timeline. And this is the discovery that should concern every single person watching this video. Not because it's exciting, because it's urgent. Every piece of encrypted data transmitted over the internet today, your banking credentials, your medical records, classified government communications, corporate intellectual property, is protected by RSA encryption. RSA works because factoring large primes is computationally impossible for classical computers. Quantum computers running Shor's algorithm at sufficient scale will factor those primes in hours. China's intelligence services are already operating under a strategy called Harvest Now, Decrypt Later. They are collecting encrypted data today, data they cannot currently read, with the explicit intention of decrypting it once their quantum capabilities reach sufficient scale. IBM's fault-tolerant quantum computer is expected to arrive in 2029. IonQ projects an 80,000 logical qubit system by 2030. The National Institute of Standards and Technology finalized its first post-quantum cryptographic standards in 2024. Apple and Signal have already begun implementing post-quantum encryption in their protocols. But here's the problem. Those standards do not retroactively protect data that has already been harvested. The window to migrate critical infrastructure to post-quantum cryptography is not infinite, and it is closing. So here's where we actually are. AI is not going away. AI is extraordinary, but AI is software running on hardware that was designed before the transistor was invented. Quantum computing is a different category of machine entirely. It doesn't process information faster, it processes information differently in ways that classical physics literally cannot replicate. The discoveries we covered today are not incremental improvements. They are proof of concept demonstrations of a technology that will, within this decade, make today's most powerful supercomputers look like pocket calculators. The question isn't whether quantum will eclipse AI. The question is whether you'll understand what's happening when it does.